Okay, so let's finish this think like a, so now I'm ready to move on to the last sort of paradigm, which is think like an embedding for pattern discovery. So here's the basic idea behind think like an embedding. So again, a single large graph, and you want to do things like a embedding. So at the end of the day, like you've seen this, right? So the embeddings are one of the key things that we need to be able to extend, right, to find the new patterns and so on. So this is a small example where you're given an input graph. Don't worry about the label for the time being. You basically start with single vertices. You basically extend those vertices by getting more embeddings. So this is just purely from an embedding point of view. I just want to show, in terms of embeddings, you need to enumerate these in any case, right? So no matter which pattern is being counted, you have to enumerate the embeddings. And so then the idea is that why don't we take these embeddings, which are much finer grained, and we want to distribute the embeddings among the machines. Okay? So it's not that you distribute the graph or you distribute the pattern, because there are many embeddings. We say every machine is responsible for some fraction of these embeddings. Okay? So you distribute the embeddings among the machines. And then so all a machine has to do is look at the embedding and pretty much do all the extensions from all the vertices in that embedding. So let's proceed forward. I mean, there are of course some challenges which I can mention, but the basic idea is that these are the possible embeddings that you can get at depth 3. But you get a perfect load balance, because what you can do is all these embeddings, right? So if you basically look at the embeddings and you say, supposing you had 4 machines, you'll basically give all, each group, or round robin, whatever, some random way that you can think of. So you got basically a bunch of machines. Maybe there are 3 machines, and you take the set of embeddings you have, the possible embeddings, and you basically assign them. You say this goes to machine number 1, this goes to machine number 2, this goes to machine number 3, this goes to machine number 1, machine number 2, machine number 3, and so on. So in other words, what we're doing is, if you think like an embedding, you say embedding is the main thing. I don't care which pattern it is. Okay? Every embedding corresponds to some pattern. Right now I don't know what that pattern is, but ultimately if you want to enumerate things, ultimately if you think from the pattern point of view, from a pattern there are embeddings, you're saying just flip the whole idea. Okay? Start from the embedding, and each embedding corresponds to a different pattern. And so you do the reverse. You say your job as a machine is just to take an embedding and to extend it. And this job is pretty much not that expensive, because I just do who my neighbors are. Okay? And each guy will just extend. And then I pretty much broadcast this information in the system, so to speak. Okay? And now the challenge, of course, is that once you do this, for every embedding, like this is an embedding 1, 2, 3, the question is, which pattern does it correspond to? So now you do like an aggregation. So basically for every embedding you have to find the corresponding pattern, and then you have to aggregate on that pattern. And so this way you'll get all the global, So what you can do then is you can prune the embedding. So once you map it from the embedding to the pattern, another embedding to that pattern, another embedding to that pattern. So now this pattern you get some value. If it's above minimum support, it's fine. If it's below minimum support, you basically say that all these embeddings can be thrown out of the system. They are no longer valid. But anything that survives, that can be equally distributed in the entire distributed system. So that's the basic idea behind think like embedding. So basically, this sort of shows you the schematic, where you pretty much say that the exploration will still go in steps. So it's still in that sort of bulk synchronous expansion. And here each step corresponds to the number of edges in the pattern. Okay, so first step is all embeddings of size 2. basically size 2 in this case is, I mean size 1 rather, like single edges. Then the next would be all embeddings of 2 edges, all embeddings of 3 edges, and so on. So every time you start with a set of embeddings, so let me probably just write it this way. You know, so if you have a graph, and now let's give these vertices 1, 2, 3, 4, and 5. Let's make that A, B, B, A. Okay, so now remember the idea is that initially, basically, if you think about the first level embeddings, this can happen completely at in a distributed manner. So all the embeddings are 1, 2, 2, 1, 1, 3, 3, 1, 1, 1. I mean, sorry, yeah, 1, 3, 3, 1, 2, 3, 3, 2, 3, 5, 5, 3, 3, 4, 4. Okay. So, and sorry, yeah, 4, 5, 5, 4. So these are all the embeddings. They can be completely distributed among all the machines, right? So now you get a perfect load balance. So you don't have the issue of load balancing that we have with things like a pattern. Because now I've taken the embeddings and I've basically split them up. Okay, so now once you have split them up, so this, let's say this chunk gets assigned to process number, machine number, so let's say P0 or P1. This chunk gets assigned to P2. This chunk gets assigned to P3. And there are only 2 for that. So if I had 4 machines, I basically split them up equally, or I do round robin, whatever. So they are assigned equal amount of work. So what is the job of this machine now? So from an embedding point of view, first of all, what it has to do is it has to figure out I sort of skipped one step, but essentially what you have to do is you have to map an embedding to the pattern. So first you have to find out, right, the sort of global computation. So you have to say that what is the pattern corresponding to 1, 2? It's actually AA. What is the pattern corresponding to 1? It will also be AA. What is the pattern corresponding to 1, 3? It's AB. Okay, what about 3? This will be BA. Okay, this is going to be a problem. Okay, we'll talk about canonicality, right? So the canonicality issue is still going to show up. So non-canonical things have to be thrown out at some point. But for now, let's just say we don't worry about that. We just enumerate everything. 2, 3 is AB, 3, 2 is BA, and so on and so forth. So you have basically, the first task is that you have to take the embedding and find the corresponding pattern. Now once you found the pattern, then you have to do a reduction. Okay, so first you map to pattern. So basically you're given a set of embeddings. You take that set, you map to the pattern. Now once you map it to the pattern, then you can do the reduction. Okay, in this reduction process, you need to be able to compute the exact support of all of them, eliminate any duplicates that you have, non-canonical things, and at the end of this, you're going to know exactly, which patterns are globally frequent, and so on and so forth. Okay, so now I know. Okay, now things that are not frequent, those embeddings can be thrown out. So if I assume that BB is not frequent, okay, so BB would be 3, 5, right? So BB you determine is not a frequent pattern. So then you simply squash those embeddings. Okay, so 5, 3, 3, 5 will be thrown out. There's no other BB. So those are not thrown out. Everything else is a valid embedding, right? Because it belongs to some frequent pattern. So AA is 1. AB, actually AA is also thrown out for the same reason. So the frequency is 1, so throw away AA. So 1, 2, 2, 1, get thrown out. And now you have a bunch of embeddings. And these survive. And so now the job is that these embeddings will now get, you have to extend them. Okay, so this can also be done in a completely distributed manner. So now you have to do, so after reduction, so this is basically step number 1, step number 2, and then step number 3 is extension. So in the extension, you basically pick some embedding 1, 3. Now remember, one machine is going to get this. Okay, so all that machine does is it says, okay, here's the 1, 3 edge. What are the different ways I can extend it? And now it's not just rightmost extension, it has to extend it from all possible directions. Because from this point, machine's point of view, this is a valid embedding and it has to be extended. So 1, 3 will be taken, and you look at, so that machine will look at the neighbor of 1, you say, okay, I can add a 2. So that's one pattern. It can look at 1 and 3. It can say 1 doesn't go anywhere else, but 3 does go to 2. Of course, 3 also goes to 4 and 5. And 1, 3, 5. So these are going to be the extensions at the next level. So this is all each machine does. Basically, gets an embedding for a frequent pattern. It basically extends it, and then redoes the whole thing again. So now everyone is doing this in parallel, completely distributed manner, right? Each embedding, everyone has extended it. Everyone maps it to the corresponding pattern, does the reduction, finds the frequency. So this one actually turns out to be a very powerful way of doing it, because number one, you don't have a load balancing problem. For most of these frequent pattern problems, you have to enumerate the embeddings anyways, so we're not doing any extra work, right? And the embeddings are the ones that are being completely distributed in the system, so you get a completely load balanced system. And this can really, really scale to very large graphs. Now, there are a lot of other challenges, of course. You have to eliminate duplicates, and this reduction step can become very expensive. The reason it becomes expensive is that, think of very large graphs. You are now actually incurring the cost per embedding of finding out who is canonical, who is not canonical. So for example, like this pattern here, and there'll be other BAs, right? So 3, 1. So normally when you think like a pattern, you just have to check once whether the pattern is canonical or not. Like the BA, whether it's a canonical pattern or not, you have to just check only once. Here, first you have to pretty much, because you want to do everything independently. You don't want to use some other state. You don't want to use any global information. So some processor enumerates this one, 3, 1. It says this is the corresponding embedding BA, and then it checks whether BA is canonical, and it says, oh, it's not canonical, so don't keep it. Okay, now this guy will do the same thing, but this is some other machine, right? So this is processor P1, this is processor P2. Now P2 has that P1 did this check already, right? I mean, you can say that I am going to maintain that information, but that's too expensive. Then you have to query someone else. Did you find this before, right? So you don't want to do any of that. You just say, let everyone handle things on their own. So P2 basically looks at 3.2, maps it to BA, and then it has to recheck all over again whether BA is canonical or not. So this way what will happen is that when the graphs become larger and larger, canonicality checking is hard. I mean, it is basically NP, it's not known to be in P. So that means you're repeatedly incurring this cost of checking canonical embeddings. So we have a trick. So the trick there is that you should not do, individually at each and every step. So the trick there is that you do a two-step process. So for example, if you try to find the canonical for all of these, you play 3, suppose this is a pattern, this is a pattern, this is a pattern, and basically think of this as A, B, B, A, B, A. So the orange is A, and so the color denotes the label. Okay. So in this case, you'll check the canonicality here, you'll check the canonicality here, you'll check the canonicality here. So you have basically 3 times you're doing the same check, right? Instead of that, what you should do really is you should do a 2-step check, which is first you do like a hash. Okay? I mean, you can compute any hash function really. So you say take a pattern. In this case, I'm just keeping the order intact. I'll say this is actually, AB. So that's AB. It was the other way around. Well, it doesn't really matter. So just keep the order, do some hashing. So this is still the BA pattern, this is still the AB pattern. So first you do a local aggregation. So I'll say the pattern BA is seen once, and the pattern AB is seen, or the other way around. BA is seen twice, and this is seen once. But then what I can do is, I can then say so instead of doing 3 times the check, I do something very fast, okay? I say this pattern actually corresponds to this pseudo-canonical pattern, it corresponds to this pseudo-canonical pattern, and this is just a linear time check. I mean, just you hash onto some value and you basically say, this pattern goes here. Now, everything that comes here, this is the representative, and now I just have to check whether these two are canonical. So I just check this is canonical or this is canonical. So in this case, of course, I just do two checks. So the AB check and the BA check, and I'll find which of them is the canonical pattern. But remember, there could have been a million of these embeddings, right? So if the graph is large, it's not just 3 of these. I'm just showing you 3, but technically there are many more edges. There can be many other AB edges, many other BA edges, another AB edge. So what you're doing is you're saying you can have many instances. You can have many embeddings that correspond to patterns. I'm not going to check the canonicality for each and every one of them. Okay. I'm first going to hash them to some cell, right? So everything that hashes to the same cell has the same, sort of code. And then only for that code I'll check whether that code itself is canonical or not. And that way I can eliminate everything that hashes to that cell. So that's kind of like the 2-level idea, and this really shrinks down the cost. So again, the point is you have to do a little bit of some optimizations, but this doesn't really change the thing like embedding paradigm. This is simply an extra computation. It's just when I'm doing the aggregation, I'm doing a 2-step aggregation rather than just doing everything in one shot. So contrast this with the other approach where you check, if there are 1, 2, 3, 4, 5, 6 embeddings, you'll do 6 canonicality checks. Here you just do 2 canonicality checks. So that's the difference between the number of times you have to do this. So you can do these kinds of things, and actually there is a whole, one can talk about this. So this is something actually that this is pretty much very recent work actually. So this Think Like an Embedding model is implemented, and it's basically available at this website. You can go and check it out. So this is the first sort of library that lets you do graph mining problems as opposed to page rank and shortest paths and the structural. So this is purely from the point of view of pattern mining tasks. So this is something that we implemented, and it's publicly available. And so in this library, the idea is that if you think like an embedding, so this is sort of, it improves upon the other packages, right? So if you do GraphX and GraphLab, Giraffe, the problem here is that, remember, this is from the point of view of pattern discovery, okay, clique finding, frequent pattern mining, graph-led discovery. Anytime you're doing subgraph-based matching in check, this library, this Arabesque library is actually very powerful because you cannot use any of the existing ones. They're too slow and they take a lot of effort to actually implement. So this library has those properties. And just to give you an idea, this is how the library is used. Just like I said, Giraffe and Spark, GraphX, they make PageRank, shortest path very easy to program. This library makes it very easy to program subgraph mining problems. So this is the responsibility of the system. This is the responsibility of the user. So in other words, as a user, you're just coding up only a few things, and the system under the hood is going to handle everything else. So it's going to handle this exploration part, that is generating all the embeddings, distributing the embeddings. So the user doesn't have to bother about how the embeddings are being, distributed in the system. It will do all the, scheduling of the embedding in the system. It will do all the automorphism, the canonicality checks for you. You don't have to worry about that. And it will do all the aggregation for you. So what the user has to define is simply these 2 functions called filter and process. So filter, as you can imagine, is basically when do you want to prune. Okay, so what is the condition, like minimum support or some other condition. And the process is kind of like what you're computing, right? The extension, for example, how do you extend? Because the system doesn't know how to extend. You just say this is how you extend, because different problems require different ways of doing it. So here's the example of how this might actually look like. So this is actually, essentially 6 lines of code to find cliques. Okay. So there is a very fast algorithm, okay, a centralized algorithm. It is not a distributed system. And that click finding algorithm takes about 4,600 lines of code, okay, to do. And it's also centralized. It's like a centralized solution. So in this arabesque framework, all you have to do is define the filter function. The filter function is actually very easy. You just have to, given an embedding. So if I give you an embedding, the first I tell you what the embedding is. Okay? The embedding is 1, 2, and 3. Okay. Now you have to first check whether that embedding is a click or not. So how do you check that it's a click or not? Well, that's easy. You basically look at the node, number 1, node number 2, node number 3, and you check whether this edge is there, whether that edge is there, whether that edge is there. Right? So 1, 2, 1, 3. 2, 3, and 1, 3. If all three are there, then it is a click. So that's essentially what this does here. So the is click check is actually very simple. You basically, and of course you're doing this in a growth manner. So you're going to enumerate all the cliques in the graph by adding one vertex, by adding another vertex. So anytime you add a vertex, you just have to say, is the number of new, so it's basically like saying that, when you do the extension, so supposing this is already known to be a click, and I'm adding number 4. Okay, so 4 is a new vertex to be added. So this works by basically saying, check whether this exists, whether that exists, whether that exists. So this is our check. Okay, so get the number of edges added should be the number of vertices minus 1. Okay, so if that condition is met, that means you've added edges to everyone else in the embedding. So that's a very quick check, and that's how you filter. If you're not a click, you throw it out. If you're a click, this will basically take care of that. And then the process is very easy. You just basically, every time you find a click, you output it. So just these lines of code essentially are enough to get you the clicks. So compare this with the sequential version. You can do motifs in the same way. And so I'm going to skip this because these are just some numbers. So I just want to show you, for example, the power of this kind of method is that if you look at the center, so these are some click discovery on certain graphs, some citation networks, some pattern networks, some YouTube networks, and this column is basically the numbers from like a centralized version. And you can see that it takes a very, very long time. And this is showing you, how many machines were used to mine these kinds of graphs. And for example, if you use 20 machines, and of course everyone is using 32 threads, and you can do this in like 70 seconds. That's something that took 14,000 seconds. So again, of course, we're doing things in a distributed manner, but it's highly parallel and distributed. So that shows you the power. But the more important thing I want to show is actually the number of embeddings that were actually found. So there are two different social networks. So we looked at an Instagram network which has about under 1 billion edges, but about 150 million vertices. And so on the Instagram, for example, and this number is very interesting. So the social network. So we use arabesque framework to mine this. So it took 6 hours to mine. In this case, it took 10 hours to mine. But look at how many embeddings we were able to actually handle, right? So in the entire space of embeddings, the system had looked at about 5 trillion embeddings in the case of Instagram, and about 8.4 trillion embeddings in total. I don't know how many patterns were found in the end, because this is so the motif problem is actually no. This would be all the motifs of size 4. So we gave the maximum size of 4. So it found all the triangles, all the edges, and all the all the chains and all patterns you can think of, all the subgraphs you can think of, up to size 4. Okay, so we gave it a maximum size, and so this just shows you that yes, we can mine them. It may take a while, but because the system sort of scales, right, it can handle very, very large things. Okay, so that's that is that. It's actually built on top of Giraffe. Yeah. So we're not really using the Giraffe library for the graph part. We are using the Giraffe as a sort of a dynamic expanding graph. So these embeddings, we basically put it onto the Giraffe system. So the bulk synchronous. So we're basically borrowing only the bulk synchronous part from Giraffe. We're not using any of its other functionality. Because we need to enumerate the embedding and things, so Jira doesn't know about those things. For the multiple graph is much easier, like I said. For the multiple graph, you can actually any of these systems can also handle multiple graphs, because you'll just think of it as a very large graph which is disconnected in many parts, right? And so what you do is you first find the mapping, and then you say these IDs, which graph ID do they come from? So you can do like go from a pattern to the embedding to the graph ID. You can do it that way. That you can do in a very you can use a trick. What you can do is you can say I'm going to maintain a distributed hash function which says which ID belongs to which which vertex ID belongs to which graph. So if you maintain that mapping, it's easy to find out.
Sir, in order to identify community, discover community from a very large network or something, what are the likely requirements for the input to that array?
So community, first you have to define the definition, right? So are you talking about cliques? Like, so you can find cliques, and then you can do the clique percolation idea that I told you, right? So first you can say, okay, let's find all the cliques up to size 5 or up to size 4, and then you can do the clique percolation. So Arabesque can be used for that, for example. But if you want to do something else, you want to find out, you want to maximize, community definition is very important. So you say a community is a dense set of, nodes, which has a lot of dense connections inside, but very few connections external, right? So now you have to start looking for these kinds of patterns. So then you have to design the algorithm for, and there are literally many algorithms for doing this kind of stuff. Because now you're thinking like a pattern, right? You're saying this is but the pattern is not clear. It's a structural definition, right? That is, first you have to enumerate something, you have to then compute the density, and then you have to find out, and then maybe the point is that can I grow it? So you really want to find the largest set of densely connected nodes that do not have many connections outside this cluster. So you just have to think about your logic, right? So the system is going to handle all the enumeration part. You have to handle the density computation part. So the filter process, you will compute. So anytime I give you an embedding, you have to compute the density of that, and you have to look at the external density, right? So the internal density and the external density. And then you're going to say, do I want to keep this or not? And then the system will extend and do so on. So yeah, I mean, using it is still, you have to think about conceptually how you're going to map it onto your problem. Okay, so in the remaining time that I have, I just want to mention one other thing, because this is very closely tied to the, this is also very sort of recent sort of, you can say that you want to do mining. And the reason I want to mention this is because this sort of brings in very nicely two issues. It brings in the label part and the structure part. So how can structure help in pattern mining? And in this case, I wanted to do approximate pattern mining. So let me tell you in what sense, and there are many other variations, but this is one of the things we can do, is that so far we've been talking about exact matching. Right? In many applications, you will not have exact matching. So what to do in that case? So here's an example. Here are the, if I give you, actually, should have been exact label, I guess. Oh no. Okay, yeah, this is just, okay. This is basically saying that if you have two nodes, two graphs, here's the pattern and that's the database. And this is actually showing you, right now I'm just worried about the structural part, right? So normally when I talk about isomorphism, we also talk about the labels. But ignore the labels for the time being, because the labels I'm going to use in the next slide. So if this is just a node, then this pattern can be mapped here. And you can flip the mappings, because you don't really care what the label is. So anyway, that would be like a one-to-one correspondence. But the reason I wanted to bring this up is that we are interested in approximate isomorphism. So the situation is as follows. So supposing, right, so you want to do a matching between a pattern and a graph, okay? And we'll make this assumption that actually labels have similarities to other labels, right? This is extremely useful for text type of application where, or some other application where, or let's say for proteins and other things, where you can say that one label is similar to another label. Of course, if it's the same, your diagonal entries are going to be, actually this is not the similarity, this is the distance. So I'm using this as a cost matrix, as a distance matrix. So it says your similarity to yourself is, your distance to yourself is 0, distance is 0, distance is 0. So the diagonal will always be 0. But this tells you how different is B from A, right? So I'm using distance as opposed to similarity. So this says the cost of matching an A to a B is 0.2. So you pay a penalty. Of course, to C is actually much worse, and so on. So the point is that if you can compute a distance score between labels, then actually I can find a pattern, a matching here, that is approximate, that it need not be an exact match, but I have to give you a cost threshold. I say that the match has to be within a given threshold. So like in this example, the A can map that A, okay, so that's a cost of 0. This C can match that C, that's a cost of 0. But I'm saying that this A, can match, this B can match that A, and this A can also match that B, and the penalty would be 0.2, 0.2 in those cases. So the total cost of this mismatch, of course in this case there is an exact match, so it's not really, I think there is an exact match, right? So A, no actually there is no, you will not find the exact match because this A and this A are not connected, whereas, so one can check whether there's an exact match or not, but this particular matching that I showed you, that has a cost of 0.4 because there are two mismatches in the labels. So the idea is that you give a threshold. You say you have a budget, okay, so this is, let's say, the maximum cost, let's call it theta, and you have to basically find a matching within theta. So now you have the ability to actually discover approximate patterns. Okay. So how would you implement this kind of approach? So the idea is that this one basically, so this is the task. So the task is you're given a graph, you're given a cost matrix C, and you're given a cost threshold. And of course you also have the frequency. So you want to find a frequent pattern that is within your cost threshold. And then mine all such patterns from your data set. So now we have sort of relaxed this pattern mining task. So let me show you an example where this is very useful. For example, it's very useful for protein, for protein structures. So in a protein structure, here's an example of a protein structure. It has these alpha helices and beta strands and other kinds of very interesting things that you can see. But at the end of the day, every a protein is made up of amino acids, and every amino acid has a label. Okay, so it has a single letter acronym that we can use, and we can actually, and this is a well-studied problem where people have defined the similarity between amino acids. They say this amino acid is very similar to this one, is very similar to that one, and there is actually a whole matrix already available. So you don't have to do any work to compute the similarity matrix. There is a very well-defined class of matrices called the PAM matrix and the Blossom matrix, and this is basically the log score of how similar is one amino acid to another. So for example, this one would say, if you look at this amino acid E and you look at the amino acid D, okay, for us, we don't really, let's not worry about the biology of the problem. It just says that it gives me some sort of a way to compute the distance between them. Okay? So obviously E is most similar to itself, but it can be replaced by something else without changing the shape of the protein. So remember, everything in the protein depends on the shape. And so as long as the three-dimensional shape of the protein does not change, it is pretty much doing the same function, hopefully. And so this matrix actually captures how similar things are. So now each protein can be represented as a graph, and every node, every amino acid is a label. So basically you have a labeled graph, and now I have basically a cost of saying how similar is one amino acid to another amino acid. And now what I want to do is the problem is the following. The problem is you go to a protein database, the huge one called the Protein Data Bank, the PDB. You take all the proteins, you convert them into, and these are known structures, okay, so for which we know the structures. There are more than 100,000 proteins for which we know the structure. So we take those 100,000 proteins, you convert them into graphs, you label them, and now you're looking for motifs. You're looking for, are there common patterns among these proteins, okay? So now you can say, just find all the frequent patterns, but use approximation, because nature doesn't have everything exact, okay? They might be slightly similar, but with different amino acids in certain places. And so the idea is that if you don't do exact, if you just do exact mining, you may not discover the motif. So by doing approximate, you can discover that much better. And so the question is, and you can do this for PPI networks and many other things. I'm going to skip that. But the thing I wanted to sort of mention was, how can we use, the structure with the label, right? So here's an example where you have a pattern on one side and you have a graph on the left. So at the conceptual level, it's actually very similar. What you have to do is you have to enumerate and embed it. So here's vertex number 1, 2, 3, and 4. 1, 2, 3, and 4. That's your pattern vertices, okay? And then you say, okay, what are my isomorphisms, right? You're trying to find matching. You're trying to find embeddings. But every embedding comes with a cost. Okay, so you say, if I take this pattern and I take the A and I map it to 10, right? I can do that. So that's the first mapping. So the phi 1 is your isomorphism number 1. It's the other way around. So this A, 1 gets mapped to what does it get mapped to? 30. Okay, so it gets mapped to this guy. So the cost would be 0.2 coming from there. Number 2 is this B. Okay, it gets mapped to the A, so the cost again will be 0.2. This 3 gets mapped to the 60, and the 4 gets mapped to the 40. I mean, you have to make sure that this embedding preserves the structure. Okay, so there has to be a cycle. So the structure has to be preserved. There can be no approximation in the structure. The approximation can come only from the label mismatches. So anyway, the cost will be 0.4 and so on. So you can and then check if there's an exact match. Can we find the ABAC? B, A, C, but this C is not connected to that A. Okay, so that's not a proper. It's not a proper isomorphism. So remember, edges have to be completely. So at first glance it looks like I should just match all the A's to the A's and all the B's to the B's. But the problem is that the structure part is not met. So you cannot, if I start from this A, B, A, but that's not connected to the, A, B, A, C, A, right? So A, B, A, that's not there, that doesn't work. A, B, A, no. So I think these are the only two you can find. So you can work it out and see that there is actually no exact match you can find, but you can still find two embeddings within the cost threshold of 0.4. So if your budget was 0.4 or 0.5, you would say, yes, this pattern actually matches this graph. Okay, so there is no exact match, but there is an approximate match with a given cost. So in some sense, the problem is very similar, because all you have to do then is take a pattern, try to find an embedding, and then compute a cost for that embedding, right? And then if it's below the threshold, keep it. If it's above the threshold, throw it away. That would be a very naive way of doing this, right? So you can definitely do that and it works. So all this sort of distributed paradigm that I mentioned, it can be applied to this problem. But here's the trick I wanted to show you, that if you incorporate certain structural information, you can actually do much better. Okay, so here's an example of using a structural property to help prune the matching. So here I'm going to use the notion of a k-hop. Okay, so I'm going to say that you can map. Okay, so intuitively here's the idea. You have a node in the pattern and you have a node in the graph. And I want to know whether this node in the pattern can be mapped to that node in the graph. Okay? And without actually computing all the embeddings. So what I want to do is I want to say, okay, start from the pattern and find out the number of nodes you can reach within k-hops. exactly k hops. Okay, and do the same thing for the graph. From that node, which other nodes can I reach in k hop? And now look at these two k hop neighborhoods. If there's a good, if you cannot find any good matches there, this node cannot be mapped there. So in other words, you have to be able to look at the structural information to get the match right. So let me just show you the idea that will make it more concrete. So assume that this is your graph. Okay, this is your pattern that you want to look for. Here's your database. And the question I'm asking is, of course you want to match the whole thing, right? But I'm saying for now we can break that down into a smaller question. I can say, can this C be mapped to that C in the graph? That's the only question I need to know for the time being. So that way I can eliminate that match if it's not a valid one. Okay, so I say, okay, my threshold is 0.5. Okay, that's the mismatch threshold. And so let's see how we can proceed. So first, what you do is you do the first hops from vertex number 2. So you compute the number of nodes you can reach within, in this case, within 2 hops. Okay, so this K is, so starting from number 2, which vertices can you reach in 2 hops? Exactly 2 hops. And remember, this is so in exactly 2 hops is going to be A to D and A to C. Okay? And so that's why I'm showing you. Within 2 hops you can reach vertex number 4 and 6. Okay, what about number 20? Do the same thing from vertex number 20. In exactly 2 hops, which other vertices can be reached? So it's obviously you can go from B to the A, that's 2 hops. You can go from the A to the B, that's 2 hops. You can go from B to that B, that's 2 hops. And so, yeah, you can also go that way, but that's still 2 hops, right? So I just want to know exactly 2 hops which vertices are reachable. So that's only 40, 50, and 60, those 3. Okay, so now you look at this and you say, okay, can I actually find a matching for the C and D with any one of those vertices within the cost threshold? Okay? So I've got the B, B, A on one side, the C and D. So actually it turned out yes. So if my threshold is 0.5, I can match this C to one of those B's, like for example, so in this case we're not looking at the topology anymore. Okay, I just look at the vertices themselves independently. I have a vertex C, I have a vertex D, I have 2 B's and 1 A. So all I'm saying is pick the C and match it to the B, you get 0.3. Pick the D and match it to the A, you get a threshold of 0.1, right? So if you look at the CB is 0.3, AD is 0.1. So there is a way of taking C and D and sort of matching it to BBA. In fact, you just have to match it to 1B and 1A, and it's within the threshold. So this is a theorem I can prove. I'm not going to go over the formal proof. I'll say that if you can do this, I cannot yet prune this match. So it is possible that 2 can be mapped to 20 so far. But now let's proceed. You do the same thing, but now let's do with hops of size 4. So which vertices can I reach from to in exactly 4 hops? So I can go 1, 2, 3, 4, okay? Or I can do 1, 2, 3, 4. So it will turn out that actually 4 and 6 are exactly the only vertices again which are reachable within 4 hops from 2. Now do the same thing with this 20, right? Because I want to know whether 2 can match 20. So if you again work it out, it turns out that 30 and 60 are the ones that are reachable with exactly 4 hops. Okay, so now my question is, can I map the D and C to the D and A? Okay, obviously the D should probably match the D because you get a cost of 0. But the A and the C has a match of 0.6. Okay, so that's greater. You might say, okay, maybe I should not match the D to do, maybe I should do match D to the A. But if I do D to the A, you get 0.1, that's okay. But then the C will go to the A. C will go to the D, that will be 0.8, so that will be 0.9 total. So that's even worse. So now there is no way I can match these 2 labels to those 2 within the threshold. And this, as I said, it's a theorem I can prove, which I'm not going to do here. That means I can now claim, just by looking at the k-hop information, right, because this is true. I mean, I think intuitively you can figure out that if you can reach within k-hop to a certain distance, from the pattern vertex, you should be able to find some matches in the neighborhood of the graph also. And this is true for all values of k. And if you have a mismatch at any given point, then I can say actually this 2 should never be mapped to that 20. Because no matter what you do, you'll never find a good embedding from that point. So this is actually the case, that actually in this case we can claim that you will never find that. So that means any embedding of this pattern into the database, C should never be mapped to that 20. So that means you must try to map it to someone else, and so on and so forth. So this is just an illustration of some of the ideas that I want to say, that you can combine sometimes the label information with the structure information to give you better pruning, and this really helps out in the case of approximate mining. All right, so I think we are done in terms of the content of the course. So, I can talk about other things. So the only other thing I'm going to mention in terms of, that we have not yet exhausted all the topics in graph analysis. So let's see, some of the, just my recapping, some of the things, and then I'll talk about the exam. So far, what have we looked at? So we have looked at basically, and this is in some sense also a review of the exam, in some sense, which I'll come back to. So this is a recap of all the lectures we have had so far. So we started out with basically structural properties. We said you have these large real-world networks, and real-world networks, they differ from random graphs. And so, what are the things that we can do to understand what the properties are? And so we talked about degree distributions, small world, sort of path lengths, clustering structures, and then so those are one thing you can do. You try to model the data in that way. But then, of course, you want to know which are the important nodes in the network, and the importance basically is depending on different criteria, like betweenness, like eccentricity, like how close you are to other things. And so that has an impact on the sort of what kind of value you can derive from the network. That which edges are weaker in terms of removal of the vertex. If you were to attack the network, it would result in a failure or something like that. So robustness, network robustness is a very important topic. That is, how do you design robust networks, real-world robust networks, for example. Or the flip side of this would be, how do you do viral marketing, right? So companies are always interested in viral marketing. So word of mouth, there's a new trend, and then how does this trend spread in the whole network? And can you do something, right? Whom should you target? Right? So the question from the marketing point of view is that if you have a large social network, which vertices should you sort of recruit to become your mouthpieces, and then their followers will immediately adapt, or adopt those ideas. So spread of information, spread of, why does a particular video go viral versus another similar video does not go viral? For videos, for tweets, so all those things are extremely important to understand. Although we didn't really talk about the dynamics, right? So we didn't really cover many of the techniques in dynamics and the spread of information and the cascading effects that we see in real-world networks. But those are all obviously very important topics. So the first one was the structural property and importance. Okay, so then we went on and said, okay, now we want to do pattern discovery, right? So that was the second topic, which sort of we revisited today in some sense. So pattern discovery was, we go beyond structure to incorporate labels. So once you have labels, now you want to find out, okay, what is happening, not just from the point of view of a single node, or from the point of view of the whole graph. So remember, these structural properties are basically of really two main kinds. Okay, they're local, that is, the information is pretty much for a node, or they are basically global. They are for the entire graph, like the average path length, diameter, stuff like that. So what the second part tries to do actually is tries to fill this gap. Okay, there is either something from the point of view of V, or there's something from the point of view of the whole graph, but it doesn't tell you anything about the subgraphs. Okay, this is basically the point of subgraph discovery / pattern discovery is basically exactly trying to fill this gap. That between the vertex and the graph, the whole graph, there's a lot of stuff going on. So what are these subgraphs? So this is the small g, basically the smaller, so these are basically patterns that are between local and global. So between so that means if you have a very large network, you're telling me what's happening in this network, right? So in this small part, what's happening. So that is the basic idea of subgraph. That's why we're going from just a vertex or the whole graph to a subgraph. Now, in here we can do frequent subgraph mining. We can do distribution of subgraph, like the graphlet, stuff. We can do clique discovery, which would be completely dense subgraphs. You can do community discovery, which would be dense subgraphs. So clique is density 1, but if you relax that to be something less, then you become a dense subgraph discovery. So all kinds of patterns can be discovered. You can discover bipartite structures, you can discover quasi-cliques, and so on and so forth. So there's a whole bunch of rich things one can do in terms of what is the local, what is the subgraph structure as opposed to purely local or global. Okay, so we talked about those things, and then these were pretty much just either models or properties of the network. And actually we didn't really talk about this, but you can use, so the models like Baravasi-Albert model, the random graph model, they were pretty much living here. But if I give you this distribution of subgraphs, you can actually use those as a generative process also. So you can basically come up with a model that preserves triangles, that preserves certain properties. So we mainly talked about degree distributions and clustering distributions, but you can also say, can you come up with a model that preserves the distribution of the subgraphs, right? So come up with a random network or a model that will give you exactly the same graph-led distribution. Can you come up with a model like that? And people have looked at those kinds of approaches. So a more generative model that captures more properties of the input data, not just structural properties, but also subgraph properties. So one can do that. So then the third thing was, okay, how do you use, this kind of stuff? So we said, okay, we can also do clustering. We can actually find groups in these networks. So that was the third part. It's graph clustering. So graph clustering, we then talked about, essentially this very tight connection. This is where the whole connection to matrices came about. So this is highly dependent on the linear algebra. Basically, graph matrices. So here we came to know some of the fundamental matrices that are associated with graphs. Things like the adjacency matrix, everyone knows. The degree matrix is easy. But then the normalized adjacency matrix, which is the Markov matrix, again a well-studied matrix, and then the Laplacian and so on. And here we basically said it's a question of graph cuts. You're basically trying to partition the network into these groups, and those partitions is what basically leads to these matrices in a very natural way. Once you model them as some objective function, the matrices just pop out of that modeling process, and that's why there's a deep connection. So the connection is with the matrix. So here the matrices are basically there are two main ideas. So one main idea is the cut, right? So the k-way graph cut is one idea. The second main idea is random walk. So everything is basically dependent on this. So random walks is one of the most fundamental. Whenever you make the matrix a transition matrix, okay, so one-step transition matrix, if you can compute, then essentially you can do all kinds of interesting things with walking over this matrix. You can do pretty much a random walk, you can do a bias walk, you can do inflated walks, right, like the Markov chain clustering that we saw. You walk one step and then you do something else. So And then there are other walks which we say random walk with restart. So essentially the idea is that you walk, and with some small probability you jump back. So we didn't really talk about those ideas, but there are random walks with restart, random walk with jumps, there are many variations of this whole thing. But the fundamental was, I showed you what the main ideas are, but there are lots of variations of this whole thing, and so they lead to different types of clustering. And then we also briefly talked about directly clustering graphs and finding things, so like the German-Newman, and then of course the click percolation. So again, we didn't really spend too much time on those, focusing mainly on the graph cuts and the ratio cuts and those kind of things. So that's pretty much. There are many other things one can do in the clustering side. And then we talked about the fourth thing. So let's call it A and B. So the fourth thing was classification. So here again, I basically tried to connect that to the kernel approaches, right? So essentially the main notion of the classification part is that if you have graphs, whether you have multiple graphs or you have a single large graph, the idea is to compute a kernel. In the one case, it's a kernel between graphs, and in the other case, it's a kernel between nodes. So there are different ways of doing that, but once you get that, you get the kernel matrix, and then I can use that kernel matrix in other classifiers like support vector machines and other things to do the classification. So I didn't really mention anything about the classification algorithm other than support vector machines, focusing mainly on how to compute the similarities, because that's the main thing. And so there we talked about the two main cases, the multiple graph case and then the single case. And in the single case it was mainly the diffusion kernel. And in this case it was basically topological, subgraph based. Right, so the idea is that you enumerate the graphlet distribution, compute a similarity based on the graphlets, or compute a similarity based on subgraphs. Topological would be compute all kinds of properties, global and local properties of a graph, path lengths, degrees, dominant eigenvalues and whatnot, and then compare two graphs based on how similar these things are. So you can define kernels between graphs, or the diffusion kernels can define between nodes. And so at the end of the day, you get the kernel matrix K, and then you use that kernel matrix to do all kinds of stuff. So that was that, and then finally we talked about the distributed part. So and this distributed, of course, is for big, when you really have large. So if you have a small graph, I mean, it would be pointless to try to do this on a Hadoop cluster, right? If you have a graph of 100 nodes, I mean, you might as well do it on a laptop or on some machine, because the overhead of Hadoop is high. So if anyone has used Hadoop, you know that if your data is small, then there is too much of a cost to pay. I mean, even a small computation is going to take you several minutes or something to run, whereas on a laptop you'll probably finish in a few seconds. The Hadoop or MapReduce on these big data platforms really makes sense when the data is extremely large and you want to use many machines to actually solve the problem. That's where the real power comes in. And that's basically where you have big data. So we really have to have big data. And the big data necessitates that we use a distributed platform. And so then you have these systems like GraphX, Giraffe, and so on. I mean, the ones that I mentioned. So they are things like vertex paradigm mainly. So you can do page rank, structural things, fairly easily on these kinds of platforms. But then they're not really suited for pattern mining. And so then I mentioned the Arabesque platform today that you can use for pattern mining. So these are mainly for for the other stuff. And then the third one will be just Arabesque. This is mainly for pattern mining. So in a way, Arabesque is sort of the first platform that makes it easy to do pattern discovery tasks, because every other platform doesn't explicitly target that, so there was a need for such a system. So they're not on equal footing. I mean, they're doing something else, this is doing something else, but they optimize in their own domain, right? So this is mainly for pattern mining, graph-led discovery, click finding, dense pattern. Anytime you have an embedding and you want to enumerate these embeddings, you can use Arabesque-like system. If you want to do other stuff like structural stuff, shortest paths, betweenness computations and so on, obviously you're not going to do betweenness computation using Arabesque. Arabesque has a very limited scope of doing pattern discovery. I mean, so there's a lot of problems in that scope, but they only solve those kind of problems. These guys are general purpose graph, so they can do pattern mining, but it's extremely hard and extremely slow, but they can do many other things very quickly. So that's pretty much a wrap up of what we have done. So the question is, what kind of exam can we have, right? So I'm sure everyone wants to know what kind of exam we can have. So the exam is actually going to follow this approach. Now, what I have in mind is the following: that the structural part, actually there are many things you can do just by hand very quickly. So supposing I give you a small graph, I can say compute the degrees of, give me the degree distribution of this graph, right? I can tell you compute the betweenness value for a node. I can tell you compute the, the closeness centrality or something like that. So those kinds of quick things you should be able to do with paper and pencil. And some of the structural properties, so basically the question will be something like, here's a small graph, it has some labels. Well, in this case, there's no need for labels. So there is a small graph, and I'll say, compute certain properties, like compute the degree distribution, compute the clustering coefficient of a node, compute the betweenness value for a node. So that will be sort of the kind of question you can expect here. If I ask you to multiply a matrix and a vector, can you do that?
Yes.
I mean, there are some no. I mean, computer scientists can do it, but there are, I think we have a mixed class of someone who, so, I mean, I'm not asking you to finish the whole, dominant, I mean, that would be too much. But if I say show one iteration of the page rank, no? I think the biology student might have problem. So I'm not going to ask that question. But the basic property computation you can do. Okay? So that I expect everyone to be able to do. Okay, so let me jump ahead then. So jumping ahead in the clustering part, you can expect a question like, here's the same small graph, compute the Laplacian matrix.
Yes, sir.
Okay, that you should be able to do. Because
Yes,
you have to compute the adjacency matrix, and you have to compute the degree matrix, and you simply subtract them, right? By the way, it's going to be open book, open notes. So you're not expected to memorize anything. Just read and understand. So you don't have to remember any of the formulas or anything. Okay, so here it will be mainly on the matrices. Okay, so given a graph, what kind of matrix can you compute? So this is so these are the questions that are sort of paper pencil type of questions where given a graph, you're doing something with it. Now, for the subgraphs, I can actually ask you to find the embeddings of a pattern. So I can say, here's a graph, here's a pattern. Find all the embeddings of this, and find only the canonical, like the distinct embeddings. Okay. So I can ask you to do that. I can ask you, if I give you a graph, I can ask you whether the graph is canonical or not. So how will you discover? For a small graph, it won't be very complex. But I can ask the question, is this graph canonical? So you have to think, can I find, the thing I explained to you, can you find another DFS code? Remember the depth first code? Can you find a code which is smaller? So maybe in a few steps you can just look at it and say whether it's canonical or not, right? So I can ask you a question like that. So that would be the kind of question you can expect from the subgraph discovery part. So I already mentioned the clustering, you can expect the matrix part. So from the classification, from the classification, it's a little bit harder, but I have to see what I can ask here. So I can say, that's a good idea. So I can say compute certain feats. So I can tie it back to another question if you want, but I can ask a new question. I say, okay, find the average path length, find the average degree, okay, and use these two as a feature, and then compute the kernel. And the kernel will just be a dot product, for example. Right? So you just have to do 3 steps. First, compute for every node. If you had, depending on whether we're doing node based or graph based, you'll compute some topological property, and then using that topological property, you'll do a dot product. You just multiply the values and sum them up. And maybe I won't even ask you to do the whole matrix. I'll say, given 2 nodes, what is the similarity between those 2 nodes using these topological values? The similarity would just be, it has this value for this, it has this value for this. The other node also has 2 different values. Just multiply them and add them up. So that would be a dot product. So essentially we are saying that we can do X transpose Y. So if you can do this, you can do the dot product. X transpose Y is simply the dot product between those nodes. Okay, and then beyond that, I might just ask some conceptual questions. So there will be like multiple choice. So I'll say, do you think that under this situation, X, Y, and Z is true? Or X, Y, So that I have to think of, what questions I want to ask. I don't have them off the top of my head. But there'll be something like as an overall understanding of the thing, right? So I'll say, under this situation, should I be using this or should I be using that? Or what are the trade-offs or something like that. I mean, like if I say, for this problem, do you think like a vertex is better, or think like a pattern is better, or think like an embedding is better? And then you have to tell me why, right? So you have to sort of say, so maybe like a small justification. So, I mean, that's all I can think of. I mean, I will not make it too hard. I mean, it's a very short course, 7 days. I don't expect everyone to become, champions immediately. So that's, let's take a break now.